2-3 minutes, just so you guys can, I don't know, relax. Maybe go get a drink of water, use the restroom, something like that. All right, is everyone back, or do I need to give you guys another minute? All right, okay, so I guess we can start. So today we're going to be talking about right triangles, and more specifically, the Pythagorean theorem. I'm pretty sure most of you guys know what this is, but if you don't know, it's when you have a right triangle, which is a triangle with a 90-degree angle. This one, 90 degrees. And then you have, this is A, this is B, and this is C. You know that for all right triangles, A squared plus B squared will equal C squared. So I know that most of you guys probably know of this, but does any of you guys know how to prove this? Oh, cool. Okay. Yeah, that's good. Yeah. Okay, so that's how we're gonna start by proving it. We're gonna. Oh, that's another way. All right, so that looks like the two ways that we're gonna we're gonna prove the Pythagorean theorem. So first we're gonna use just like simple areas, and then the second proof we're gonna use we're gonna use similarity. All right. So the first one that a lot of you guys are talking about is square and a square, which I'm not great at drawing squares, but let me try to draw an accurate square. All right, so this is the first square, right? And then inside of the square, we draw another square. Okay, well, it doesn't look much like a square, but let's just pretend that it's a square. So these are 90-degree angles, and these are 90-degree angles. So let's say that this is A, and this is B. Yep, you got it. Who is it? Jane, I think? John. John? Yeah. Isn't this in the AMC 8? Yeah, it is, but the Pythagorean theorem can be used in a variety of problems, from anywhere to the AMC8 all the way to like whatever. Like, it's really useful to know, and it's really useful to be able to think about how we got the Pythagorean theorem and how to use it effectively. And there's a lot of harder AMC10 problems that utilize the Pythagorean theorem. All right, so let's say this is A and this is B. And since it's a square, all of the sides should be C. And there should also be A, there should be B, there should be A, there should be B, there should be A, and there should be B. Right, does that make sense? Simply because when the triangle splits them, and when the smaller triangle is put inside the bigger triangle, these triangles will all be the same. This triangle will be the same as this triangle, will be the same as this triangle, will be the same as this triangle. And we can see this pretty easily when we do some angle chasing. Like, let's say this is alpha, and this is 90 minus alpha, and this is alpha. And using like congruency, these are basically the same triangle, right? So we got that out of the way. We already assigned each of the lengths a variable. So I hope that sounds good to everyone, right? If you guys raise your hand, I don't think I'll be able to unmute you or something, but if you want to type it in chat, that's okay too. So there are some questions that involve a square inscribed in a square, but they don't involve this area proof. Yeah, there are lots of square inside squares problems, but this area proof is to just let you think about the triangles and how Pythagorean theorem works. It's like, I don't think it's good to just have a theorem and memorize it and just use it. I think it's good to be able to know how it is and know what it came from. Just because in the future you might see problems that are not the Pythagorean theorem but still involve squares and squares, and it's just useful to know how to think about it like that, I guess. All right, so we're going to be talking about the area of each individual piece, right? So this whole area of the big square is a plus b squared, just using the area of a square. And then the insides can be separated into each of these four darker triangles and the middle square, right, which is c squared, plus each of these four pieces is 4 times AB over 2, just by triangle area formula if you know it. It's just height times base over 2. Right, and then if we expand this algebraically, we get a squared plus 2ab plus b squared equals c squared plus 2ab. And we can cancel out the 2ab to get a squared plus b squared equals c squared. So really this works for any triangle because, any right triangle, because when you position the square inside of the square, it's not really a matter of which angle you put it in, so it works for all of the right triangles, not just the specific case. And it also works for any A, B, and C as long as they're the side lengths to a square inside of a square, right? So I think that makes sense, and this is a pretty easy way to see how the Pythagorean theorem works and where it came from. I think this is the simplest solution, and the next solution that we're going on to is similarity. So I think somebody else mentioned this, and it's when you have a right triangle, right, and you draw from the right angle to the hypotenuse. I think that's what somebody said. Let me see. Yeah, you could draw an altitude from the right angle, right? So let's look at this for a minute. We know this is A, or actually let's label this. This is A, B, C, and let's not use, is this some, let's not use the variables. Anyways, so let's call this D. So we know that using similarity, or actually first let's angle chase. This angle is angle alpha, so this has to be 90 minus alpha, right? Because of the big right triangle. And if this is alpha, this is also 90 minus alpha. And seeing that the angles are all the same, we know that ABC, triangle ABC, is similar to triangle ADB, right? And let's look at the smaller right triangle. This is 90 minus alpha, so this one has to be alpha. So we know that this is also similar to triangle BDC, right? So that looks pretty good. And then if we use, let's say AB over, wait, here. Let's actually take the area of ABC over AB, squared is equal to the area of ADB over A. Actually, do you guys know that the area of a triangle in similarity is like proportional by the square? I don't want to do a similarity class right now, but I think most of you guys already know. So if you have any questions, I can go over it in a minute. But if you don't have any questions, we can just use it. Does that make sense? Like, I think most of you guys already know what that is. Area is the area of the square halved. Oh, no, that's not what I meant. What I meant was, if we have two similar triangles, right? Let's say that this is X, Y, Z, and this is A, B, C. Okay, so we know that this is like X and this is A, right? And let's say that these triangles are similar. We know that the area of X, Y, Z over the area of A, B, C is equal to X over A squared. Does that make sense? Like, is this something that we need to go over, or is this something that you guys already know? Oh, you did not know that? Okay, that's okay. All right. So I think it's nice that we can just go over it. Let's say that this is A and that this is AX and this is B and this is BX and this is C and this is CX, right? Just because they're similar, that means that each of their sides are proportional by X. Okay, do we get this step? Okay, I'm just going to take silence as that's good. So when we find the area, we find that this area is AB over 2 and that this area is ABX squared over 2 again. So the ratio of the area of XYZ to the area of ABC is X squared to 1, while the area of the side length is AX to A, which is X to 1. So basically this, okay. This is XZ to AC, and this part is the area of XYZ to the area of ABC. Right? So we can just take this back, and instead of X over A, it will just be X over 1. Right? Does that make sense for whoever didn't already know this? It's a pretty fast explanation because we're going to be using it, but it's okay, right? Okay, you don't get any of this? All right, so let's take this slower. Let's say that when we have two triangles that are similar, right? Two right triangles. These angles are the same. And that also means that X, Y, Z, A, B, C. This also means that AB over XY is equal to CB over ZY equal to CA over XC. Does that make sense? All right, that's okay. Let's find some real life examples, right? Or not real life, but just numerical examples. Let's say that this is 3, 4, 5, and this is 6, 8, 10. So that means that these are similar triangles, right? Because each side is proportional. Yeah, basically, except it's area, not volume. Volume would be cubed. All right, so if these are, similarity says that if these sides are proportional, like they're all multiplied by 2, then these angles would be the same, right? These angles are the same, and then these angles are the same. Is that right? Also, they also said that if these angles are the same, then the sides would be proportional. So if the sides are proportional, then the angles are the same, and if the angles are proportional, then the sides are the same. Because they're like factors. Yeah, basically, they're like factors of each other, I guess. So anyways, that brings us back here. So AB over XY equals CB over ZY equals AC over XZ. So putting that in like simpler terms is, if the side is A, B, and C, the side would be AX, BX, CX for some X. It's just the factor, right? X is just the factor that it's multiplied by for each part of the triangle. Okay, yeah, that's good. So let's just say that we have these triangles. The area of this one is AB over 2, and the area of this one is ABX squared over 2, right? So the ratio of these is x squared, or the factor. So the area of ABC over the area of XYZ is 1 over x squared, right? That makes sense? Okay, so that makes sense. We also know that each of the side lengths is, like, for example, AB over XY is equal to 1 over x, right? Or C over CX, which is 1 over x, which means that the ratio of the areas is the square of the ratio of the sides. Right? That makes sense? Okay. So if we know this, and then we go back to our original thing here, let me just erase this part. Okay, so for those of people that want to get to the problems and think that this is too easy, just wait a little bit. After we finish this proof, we'll go immediately to the problems. All right, so let's look at these areas. The area of ABC over AC squared is equal to the area of ADB over AB squared. And we know this because if we just rearrange this a little bit, we get that ABC over ADB equals to AC squared over AB squared, right? And then let's use, right, so ABC to ADB is AC to AB, which is basically what we had back here, right? This area to that area is the square of those things. Anyways, now that we know this, we can see that this is also equal to DC over BC squared, just because we can see that it's similar as well, and then using the same logic. And then we also know that ABC is equal to ADB plus BDC. So ABC equals to ADB plus BDC. And then looking at this, we can see that this is A squared equals AB squared plus BC squared, because their ratios. Does that make sense? Like ABC over AC squared equals ADB over AB squared, which means that ABC or AC squared is like a factor of ABC, and we just find the factors here. Does that make sense? That we get this? All right. Okay, yeah, so that's good. So this is our second proof of it using similarity. And similarity is actually pretty useful, but that's not what the class is about right now. Or we might go over it later time. I didn't plan on it, but maybe we should. But right now, we're going to go on to the problems that you guys like so much. I think we don't have as much time anymore, so we're going to skip some of the easier problems. Here, let's see. Actually, well, this one's pretty easy, but I like this problem. Yeah. I'll just let you read it. It's not that long, so we can get started pretty quickly. One hundred and 119 is close. It's close. Yeah, so a lot of people are saying that it's 169. All right, so we're just gonna go over this pretty quickly. So what we already have is, let's say that PR squared equals PQ squared plus QR squared by Pythag, right? This is by the Pythagorean theorem. And then if we look at it, we also see that the PR squared equals PQ squared plus QR squared is also the sum of the areas, right? So PR squared plus PQ squared plus QR squared equals 338. And if we substitute this here for PR squared, we get that 2PQ squared plus QR squared equals 338. And then PQ squared plus QR squared equals 109. And then we plug this back in, we get that this is equal to PR squared equals 169, which is the area of the larger square. Does that make sense? This is a pretty simple introductory problem. Most of you guys got the right answer, and I think we can be moving on, right? Just put a yes in chat if you guys think that this is good to move on. All right. Okay. Thanks, Tanya. Okay. Can you go over this more thoroughly? All right. It was just an application of Pythag though. Here, let's say that this is A, this is B, and this is C. We know that A squared plus B squared equals C squared, right? Just by what we had before, by Pythag from before. And then if we look at this, we also note that the area of the square, PQ, is A squared. And then this one is B squared and this one is C squared. So A squared plus B squared equals C squared equals, or A squared plus B squared plus C squared equals 338 because of what it says here. The sum of the areas of the three triangles is 338. And then we also know that since A squared plus B squared equals C squared plus C squared equals 338, and 2C squared equals 338, so 1C squared equals 169. And since that's the area of the largest square, we get that C squared equals 169. Okay, yeah, that's good. All right. I think we can skip that one. I think we can skip these two. All right, we'll just skip these two. Right, let's go on to this problem. This is the next problem. I'll give you guys a minute to look at it, and then we'll go over it. All right, that's okay. It looks like nobody has an answer yet, but I think we should go ahead and try to solve it now. All right, so we skipped a lot of the easier problems, and if we have more time in the end, we can go back to them. But I kind of wanted to solve this question because it's a nice problem. And then after we solve this, we can go back to a couple of the more easy problems before the next problem. All right. I think a couple of you guys are getting the answer. Yeah, 84. 84 is the right answer. That's good that you guys can get this. Okay, so in quadrilateral ABC, right, so this is my best attempt at a right triangle ABC. And then diagonal AC is perpendicular to CD. Right, so this is our quadrilateral, ABCD. This is a right angle, and this is a right angle. So we know that AB is 18, and BC is 21, and CD is 14. Well, AC squared equals AB squared plus BC squared. There. And then, which is equal to 18 squared plus 21 squared. So AC, this one, AC equals square root of 18 squared plus 21 squared. We're not going to simplify this right now just because it doesn't seem necessary, right? So we can just leave it like that. And now for AD squared equals AC squared plus CD squared equals AC squared plus 14 squared equals, and when we look at AC, we just find that it's the square root of 18 squared plus 21 squared. And if we square this plus 14 squared, it's equal to 18 squared plus 21 squared plus 14 squared. Right? And we don't know what this is, but if we just do a little bit of arithmetic, can anybody tell me what this is? Or right, okay, it's okay. Oh, 934? Question mark. Oh, 961. All right, let's go and look at it a little bit. We have 324 plus 441 plus 196. You can solve this out, but I'm pretty sure this is what it is. And if we add it, we get 961, I think. Is that what you guys got? 961. Oh, okay. Yeah, so that looks pretty good. So AD squared, whoops, equals 961. And I don't know if you guys can remember this, but if you square root 961, you get to AD equals 31. You can multiply it out for yourself if you don't believe me, but this is what we're getting. And we're not finished yet though. If we go back and see this, we need to find the perimeter, which is AB plus BC plus CD plus AD, and this is only one part of it. But luckily, the rest of it is given to us in the problem. So if we add this all up, we get 84. Yeah, 84 looks like the right answer. Is that good? Is that good for everyone? Yeah. Okay, so let's think about the two problems that we just did. Oh, how did you divide 961? You just know that 31 squared is 961 just based off of, I don't know, like a bunch of practice and just doing math repeatedly. But if we want to find an easier way to see that 961 is 31 squared, we know that 900 equals 30 squared, and this is more than 900. So if we just try, we can get the 31 squared equals 961. I wish that they have pictures. Yeah, my drawings aren't really great, but most of these questions did not come with pictures. But maybe we can do the next question as a question with pictures, right? But before that, I wanted to ask you guys, do you guys think that this one was really hard or the other one was really easy? I want to get your feedback on these two problems because they're kind of at different ends of the spectrum. The other one was kind of easy, and this one was a little bit like towards the harder section. It's not super hard, but it's like around the level of where middle AMC10 might be. So I just wanted to get your feedback on how it is. You just need pictures to solve it? Oh, do you mean like after you saw my picture, it would be easier to solve it? Or after you draw your own picture? Yeah, the question doesn't really specify how the picture would look, so it might be a little bit hard to get the idea of what the quadrilateral is. Yeah, it's really easy with pictures. Once you draw the diagram, you'll be able to figure it out easily. Yeah, so in a lot of geometry problems, they won't give you a picture, but like it's really important for you to be able to draw accurate diagrams and to read the instructions carefully, because having a good picture or drawing it out really well is like half of solving the problem. It's like really easy once you get the picture. Yeah. or once you get an accurate picture. So this one was challenging but doable, and both were kind of easy. All right, okay. So it's good that this one's not too hard for you guys, because this is basically what you're going to be seeing mostly on the AMC10. Maybe a little bit easier than this actually, if we're talking about early to mid AMC10. But if we're talking mid to late, this is like relatively around that level. It is very easy even without pictures. Oh, yeah. Well, congratulations, you're pretty smart. Yeah. So we're actually gonna go back to one of the previous problems. Let's see. Oh, okay. Actually, well, maybe we want a problem with pictures. All right, let's look at this one. This one's pretty easy. I think it's easier than the first problem that we did, but it's a nice one with a nice diagram, and I'll just give you guys like a couple seconds to think about it. Yeah, 21.6. Yeah, I'm pretty sure that's what it is. So a lot of times in competitions, you won't need to be you won't need to put it in decimals, and just leaving it as a fraction is pretty good too. In AMC10, they'll give you the answer choices, and most of the time the answer choices will be fractions, but it's not too difficult to convert it. But in Amy, if you're going to be solving it, it's going to be in fractions most of the time, but it'll ask you to like add the denominator and numerator or something. So it'll be an integer, but just keeping it as a fraction is pretty good as a general rule. You can make it a 3, 4, 5 triangle and do a proportion. Yeah. All right, 108 over 5. Yeah, that's kind of what I was looking for. All right, so to start this, we can introduce that this is 3, this is 4, and this diagonal is the square root of 3 squared plus 4 squared equals the square root of 9 plus 16 equals square root of 25 equals 5. So normally you don't need this long step to get a 3, 4, 5 triangle, because we have Pythagorean triplets, I think, or yeah, trios, triplets. All right, I think that's it. So common ones are 3, 4, 5, 5, 12, 13, 7, 24, 25, and the list goes so on. Do you guys know any more that we should add? I think these are the basic ones, but there might be more that's commonly used. I don't really remember. Oh, actually, yeah, 8, 15, 17 is also pretty important. Yep, 21, 20, 21, 29, right? So these are triples. Oh, 11, yeah. 11, 60, 61. This is like never used. I don't really use this one a lot in competition math. It's actually mainly these 3 that are used a lot. But yeah, these are like common ones. If you don't trust me, you can multiply it out and add them up. But these are ones that you should basically know for competitions and stuff, just because it's easier to remember them rather to, you know, square everything and then add them and then like square root it. So I think it's pretty good to be able to remember most of these. Yeah, so these are Pythagorean. I don't think they're triplets actually. I think they're called I don't know what it's called. I don't remember. But triples. Yeah, triples. That sounds pretty correct. All right. So okay, so it's 4 to 3 of a 27 inch. So we know that the diagonal is not 5 and is actually 27. But going back to our similar triangles, we know that if this is 3x and this is 4x and this is 27, we know that this diagonal is also 5x. So if 27 equals 5x, x equals 27 over 5. And the horizontal length is 4x, which is 4 times 27 over 5 equals 108 over 5. So yeah, I'm pretty sure this problem was pretty simple for most of you guys, but I just wanted a chance to talk about Pythagorean triples and what you should have basically not memorized, but like you know them pretty well. Actually, do you think there's more triples that you guys see commonly in competition stuff? I think this is most of them. I don't think there's more exactly. I know there's a lot of groups that you can memorize that's not integers, but we're just going to be talking about integers today. We don't want to get into all of the sines, cosines, tangents, and stuff. Yeah. So I think I'm going to go move on to the next problem unless anybody has any questions. But if you're good to move on, you can just put a yes in chat and we can go to a harder problem. All right, thanks, Ishan. Right, so maybe we'll do this one. The diameter of, well, you guys can read it yourself. I'll give you like a minute. Which is the center of the circle? I'm not sure exactly what you're trying to say. But when we'll be solving the problem, I don't think the center. Oh, which point? None of these points are the center of the circle. I don't think the center of the circle matters too much in this problem. But yeah. Oh, you want a picture? Well, you're gonna have to draw one yourself first before I draw one. Yeah, it's good to practice drawing diagrams, especially for geometry problems, because diagrams are really important to the problem. What side does the line extend to? It doesn't really matter. It could be both. It's just if you extend it to like the left, you can just flip it over and it'll be extended to the right. Like if it was if you have the circle and you extend it this way, it's the same thing as this one just flipped, right? but the points are different, like the order of the points. That's true. That's true. But also, if you have this, you can just write A, B, D, or you can have A, B, D. So it's just flipped, I think. I don't think there's any other like restrictions. It doesn't really matter which side you extend it to. And I've been seeing some answers in chat, but I don't think I've seen the correct one yet. I'll give you guys a hint. It's a fraction. Yeah. So maybe, do you guys want me to just solve it, or do you guys want a little bit more time to think about it? A little bit more time? All right. Okay, that's okay. I'll just give you guys a little bit more time. Yeah. Man, we're not going to get to most of the questions that I had today, but that's all right. They were all a lot easier. These are some of the harder questions. Would you guys in the future want me to continue doing like problems of this difficulty, or rather problems that are like a little easier? All right. I'll try to find these harder problems. For a lot of easier, that's all right too. We can go a little bit easier. I think the problems that were that we were solving before were also good as well. I think this problem is one of the harder problems, especially. It's definitely not mid AMC10 level. I think maybe a little later AMC10. Easy. I want to get to know the standards. That's all right. Easier, yeah. Most of my problems are easier. We're just going over a harder one right now. Yeah. This question was and I think problem 22 on the AMC 10. So it's quite a lot harder than what you'll be seeing on like the middle parts of the AMC 10. But I just wanted to let you guys see a usage of the Pythagorean theorem in harder problems, because I know you guys use Pythag for a lot of easier problems too. Oh wait, you guys have been putting in answers. All right. I think there are no radicals in here, no square roots, but I think 3 and 29/37 is correct. I don't know why you decided to put it in mixed format though, but I'm pretty sure that's right. Yeah. Unless you meant 329, which in that case it's wrong, but if it's a mixed number, then yeah, that's right. Oh, harder problems. All right. Good to know, I guess. I don't think I'm going to be giving you guys harder problems, but yeah. I think this is like the hardest problem that I'm going to be showing you guys today. All right, I think it's pretty good to start because we have one person who got the answer already. So, let's say you have a circle and the diameter AB extended to 140/37 is the correct answer. That's at least the format that I have it in. D. Okay, this is 2, and this is 4. Or no, I think it's 3. Right? And it says that point E is chosen such that ED is 5, and the line ED, and the line ED is perpendicular to AD, and segment AE intersects the circle at some C between A and E. Okay, so let's just look at this for a minute. If we draw this, we know that this is a right triangle. I don't know if you guys know this, but if you have any triangle with the diameter, it's a right triangle in a circle. Like any of them. I think this is a good rule and a good thing to know, just because I'm not going to go too deep into explaining it, but since this faces an 180-degree arc, this is 90 degrees. Yeah. So we're just going to ignore that for now. Just know that this is a 90-degree angle. Well, I'm not sure what you're trying to say, Chase, but 74, right? That looks like a nice number. Let's find AE. Maybe it'll have something to do with 74. AE squared equals 7 squared plus 5 squared, right? Equals 49 plus 25 equals 60, 74. Right, so this is square root 74. That's what AE is. Now, I think we should use a little bit of similarity, right? Should we use similarity, or do you just want to not use similarity? I think similarity is pretty essential here. So if we look at this, we know that AC over AB is equal to AD over AE, right? Does that make sense? Can we see the similarity? It's right, AC over AB equals AD over AE. Yeah, that looks pretty good. Nobody has a problem with that, right? All right, so if we plug in numbers, we get that AC, let's call this X over AB4 equals 7 over square root 74. So X equals 28 over square root 74. Does that look good? Oh, 10 times square root 74 over 3. I think you're looking at a different side length. Yeah. 28 over square root 74 is what we have right now. Now, if we want to find y, we know that this is also equal to CB over ED. And if we put this is also equal to y over 5. And we find that y equals 35 over square root 74, I think. Oh, wait. No, sorry. This is wrong. I don't know what I was thinking. I had a bit of a brain freeze. Yeah. What I actually meant to do was CB over ED equals AB over AE. That looks right? So CB is y over ED 5, y over 5. God, my pen stopped working. Give me a minute. All right, okay. Y over 5 equals 4 over square root 74. And if we look, this is y equals 20 over root 74. Right, okay, that looks a lot nicer than the other one. So x and y. If we try to find the area of ABC, we know that it's xy over 2, right? ABC equal xy over 2, just based on triangle area formula. And if we look at this, we know that it's 28 over root 74 times 20 over root 74 and over 2, right? And if we look at this, it's 28 times 20 over 74 over 2 equals 28 times 20 over 74 times 2 equals 28 times 5 over 37 equals 140 over 37. $28 times 20 over 148. Yeah. So basically, you just have to multiply it out to get to here. It's just arithmetic, so I don't think I need to explain it. But it might be a little bit hard working with the radicals and multiplying and dividing with radicals. But yeah, does anybody have any questions on how we got here? I think it's pretty straightforward once you draw the diagram and write out the similarities. But if you guys need anything explaining, we'll go for it. And since we only have 4 or 5 minutes left, just put like a yes in chat if you think this is okay, and then we can go on to an easier problem. Oh, Edward, do you have a question? You can just a yes in chat. Okay. All right. So this is a harder. Yeah, it's all right. This was a harder problem. I don't think we'll be able to have time to solve this problem, but I'll send the document to Rich, and I think he'll put it on the Kid Teach Kid website, so you'll be able to find it, and I'll include the answers as well, so you can get the answers. If you need to know the solution, I think most of these problems you can find it online, but if you really need to know the solution, you could probably email me, and I think my email is on the Kid Teach Kid website as well. So yeah, I don't think we'll have time to solve this problem. Or actually, maybe we do. 5 minutes. Do you guys want like a 5-minute like easy problem, or like a 5-minute like harder problem? Easy problem. All right, let's go to find an easy problem. Oops. Okay, look, this one's pretty simple, and I think we'll have time to do it. Okay, so I'll give you guys a couple seconds to look at it. I don't think it's too hard. $24, yeah, 24 is good. Okay, we can start solving this problem then. So we know that AC equals 13, and AB equals 15, and CD equals 5. All right. If we look at this, we remember that, what do we remember? Oh, we remember that, 5, 12, 13 is a Pythagorean triple, right? Do you remember that we said this? We know that 25 plus 144 equals 169. Yeah. So this is 12. And we also know that 12, 15, something. This isn't a Pythagorean triple that we went over before, but we can see that this is basically a 3, 4, 5 triangle just multiplied by 3. So it's 9, 12, 15, right? So this is 9. And so, what are we looking for? Oh, AC. Right. So if we know that this is 9, then this must be 4. And the area, oh, no. Right, okay. I'd rather you not spam in chat. Can you say what you have? Can you say what you need? Oh wait, you're just saying that 54 minus 30 equals 24? Yeah, that's true. Okay. But anyways, so this is 4 and this is 12. So an area of a triangle is basically the base times the height, which is 4 times 12 over 2 equals 24. And we see that this is the base and this is the height of the triangle here. Yeah, 24. All right, so it's 5:59. I think we're basically done here. If you have any questions about any of the problems, just let me know and then we can go review it. But if we go review it, it just might be a little bit late. Yeah, but if you get it, you're free to leave. Also, if you were here last class, I just want to know if you think that the difficulty of this class was harder than last class or easier, or if you think you want me to go slower or faster. Just any kind of feedback is good. Yeah, that's true, David. That's true. Harder and slower. So more hard problems, and you want me to take more time explaining these problems? All right. Um, yeah. Also, in comparison to the last class, do you think it's better in terms of difficulty, or do you think last class was easier, this class was harder? Oh, okay. So this class was harder, and you want me to go slower? Yeah. All right. I think today I was just trying to rush and get a lot of problems done, but next time I'll be able to explain it better, I guess. Yeah, if you have any questions about any of the problems, don't worry. Just tell me and then I'll explain it more. Even if you see like other people can understand it and they get the problem, but you still have questions, don't be afraid to just raise your hand and speak up because everybody is on different levels right now, and I don't expect you guys to be the same. Like if somebody gets a problem but somebody else doesn't get it, I'll try to stop and explain for them because some of you guys are more ahead and some of you guys are slower. Thanks a lot. Bye. Yeah, bye. It's 6:01 already, so you guys can leave. All right. Um